put together all of the sciences to arrive at an understanding of the way in which the Earth works. My background is that I spent a few years working on oil rigs, and I also taught geology and geography for 26 years. But don't worry, it's not a lesson. There won't be a test at the end. So what are we looking at today? Well, I'm hoping to give you an understanding of how the science of geology works. So with apologies to those of you that attended my talk yesterday, I'm going to use this little bit about which I used in the Earth structure talk again, because being a geologist is very much like being a detective, but rather than turning up on the day of the event, if there's been a murder, you're turning up millions of years later, and most of the evidence is now missing, and what is there may well have been altered in some way. And like detectives, in order to get to the root of to the nub of the problem, we need to ask the right questions. So with this, we might be asking these sort of questions. So what happened was that a parked car was hit by a rock weighing 12.5 kilos. Where did it happen? Peekskill, New York, United States. When? On the 9th of October, 1992. Why did it happen? This was a meteorite impact. The person that was affected was the owner of the car, Miss Michelle Knapp, and her car was a 1980 Malibu Chevy. It was only worth about $500, but she managed to sell it to a meteorite collector for $10,000, and it then went off on a world tour doing all sorts of exhibitions about meteorites. More of which later. What I want to start with is an enigmatic explosion. Oh, perfect timing. So on June the 30th in 1908, there was a weather station in Cambridge in the UK that noted a sudden change in air pressure. At 1 o'clock in the morning, there was a flash of lights in the sky. 4 hours later, there was a rumbling, a thunder, if you like. Now, light travels faster than sound, so that event was a very, very long way away. Thousands of kilometers away, hundreds of kilometers away, sorry. And 60 kilometers away from the event that sparked the drop in air pressure, the flash, and the thunder, there was a witness in a place called Tunguska. And the witness was quoted as saying, "There was a bang in the sky and a mighty crash followed, by the noise like stones falling from the sky. The earth trembled. It appeared to be Armageddon. I became so hot I couldn't bear it. It was as if my shirt was on fire. And then the sky slammed shut and I was thrown a few yards." So obviously something pretty big had happened. This event happened just before World War I. It happened in a very remote and very sparsely populated area of Siberia. So not a lot of people go there. And it wasn't until 1927 that a Russian scientific expedition went to investigate, see what on earth had happened there. What they found was this: 80 million trees smashed down over an area of over 2,000 square kilometers, but no apparent impact crater. And for a while they thought, oh, was it a nuclear spacecraft or something? No, no radiation. On very close investigation, looking at some of these trees that had been flattened, they found tiny fragments embedded in those trees, evidence of a meteorite between 60 and 160 meters diameter, ballpark figure, think size of the Albert Hall. It didn't actually hit, it skimmed. So it exploded high in the atmosphere, maybe 5 to 10 kilometers high, and that's why there weren't all that fragments. Might have looked something like this. So what we've got then is a sizable meteorite, possibly, well, wildly varying estimates of how much it would have weighed, but with a significant amount of energy, anywhere between 10 and 40 megatons of explosive energy equivalent, of a TNT equivalent, a megaton being 1 million tons. So that's a big bang. So what would that have been like? Cast your mind back to February the 15th, 2013.
It was in February when the meteorite exploded over Russia's Ural Mountains. The falling space rock provided an enlightening morning rush hour view for motorists, with flashes of light in the sky above. Those lucky enough to have dashboard cams caught the fireball, but the meteorite scattered into pieces, causing damage to buildings and injuries.
So, quite exciting. But if you compare the two events, the Tunguska event was much, much bigger, many orders of magnitude bigger. So what would happen if you had an event like that in London? Well, if a meteorite of a similar size to the Tunguska event hit London, the footprint of destruction, if you like, that inner zone, the red circle, that would be total destruction, an area of maybe 10 to 15 kilometres across. But pretty much everything inside the M25 would undergo a great deal of damage. If a similar meteorite landed in the Atlantic Ocean, we'd get a huge wave, a wave formed by the displacement of water, effectively a tsunami, which would devastate coastal cities all the way around. But what about if we had a bigger meteorite, maybe 10 kilometres? We'll consider that a little bit later. First of all, let's consider what meteorites actually are and where they come from. So my little cartoon at the beginning helps with this. So an asteroid is a rocky object deemed not to be big enough to be a planet, and they orbit between Mars and Jupiter. And there are hundreds of thousands of these things, the biggest of which may be a couple of 100 kilometres across, but many of them are considerably smaller than that. They originated as the remnants of the early formation of the solar system. So the solar system forming 4.6 billion years ago with the rotating cloud of dust and gas, a rotating nebula. And this coalesced into larger bodies and then formed the planets and the asteroids. So, another little bit of excitement. There we go. September the 24th. There we go. So that was an actual direct sampling of an asteroid, very exciting for geologists, and gives us further information about that material. So if you get a small asteroid or a fragment of an asteroid entering the Earth's atmosphere, then there will be an enormous amount of friction and a great deal of heat. And most of them burn up on entry into the Earth's atmosphere. And this is where we see a meteor, a shooting star. A bright streak of light, which varies in brightness and could last for a fraction of a second or sometimes a few seconds. A comet is mostly ice and dust. A meteorite is when the object actually reaches Earth. So, here's a meteorite. They're actually very common. Most of them are tiny. There's a constant rain, if you like, between 40 and 80,000 of these things a year. Most of those may be smaller than a pea. But we do get somewhere between 20 and 80,000 a year that weigh more than a pound coin, so maybe more than about 10 grams. But we don't find them very often. Most of the planet, 71% of it, is covered in water. So if they land in the sea, we're not going to find them. If they land in an area of vegetation, they're going to be very difficult to find. But you can find them in areas like the Arctic, the Antarctic, and in desert areas. So the moon, rubbish tourist destination, got no atmosphere. But because it's got no atmosphere, there is no weathering, there's no erosion. And that means that all of the meteorite impacts on the moon are preserved. That's why it's pockmarked with all of these impact craters. On Earth, many of them would have landed in the sea. And because of plate tectonics, the way in which the plates move, there's no oceanic crust older than roughly about 200 million years. So maybe there have been plenty that have landed in the sea, but those impact craters have since been destroyed. So we know a little bit about meteors, meteorites now. Let's think about dinosaurs. What are they and why were they so successful? They're a very diverse group of reptiles. They were around in what's known as the Mesozoic era, between 252 and 66 million years ago. And they ruled for a very long time, for a variety of reasons. They were very widespread. Between 300 and 200 million years ago, all of the continents were joined in what we call a supercontinent called Pangaea. And this made it possible for dinosaurs to move between climatic zones. And indeed, they evolved a wide range of adaptations and thrived in all of the climatic zones. Some of the dinosaurs grew to huge sizes. So sometimes with geologists, they're a bit pernickety. We always have to have something for scale. So here we go with an elephant for scale. So the advantage of being big would be that you could avoid predation. You'd be difficult for things to kill you and eat you. But also, if you've got a very long neck, if you're a herbivore, you could access food resources that other herbivores could not. And being reptiles, that needing to regulate their own body temperature, being big counts. Much easier to regulate your body temperature if you're very large than if you're very small. Many of the dinosaurs were actually bipedal, walking on two legs, and the advantages of this were speed and agility. If you've got long legs, if you've got a sort of a bird-like pelvis, I mean, if you think an ostrich can run at 70 kilometers per hour, that made the bipedal dinosaurs very efficient at running away or running to catch things. Some of the dinosaurs exhibited quite complex social structures, we think, so quite similar in many respects to many birds and mammals in that they cooperated. There's fossil evidence that they actually hunted in packs and also that they moved in herds, moving in a herd to protect the old and the weak and the young. They evolved varying strategies to ensure the survival of the young as well. So there was probably a degree of parental care. They certainly nested, and there have been fossils found of dinosaur eggs, a clutch of eggs in a nest. And they also were almost certainly camouflaged, which is why you don't find them in the Caribbean. Despite the adaptability and success of these marvellous creatures, and 166 million year reign throughout the Mesozoic, when we get to the boundary between the Cretaceous period and the Tertiary period, what we refer to as the KT boundary, they became extinct. Now, when geologists talk about eras and about geological periods, these lengths of time are marked by significant geological events. And the eras are marked by mass extinctions, when large numbers of unrelated organisms disappear. So, with this extinction, it wasn't just the dinosaurs that became extinct. Now, as well as the dinosaurs, you can see bottom right there an example of an ammonite. Now, I've been a passionate geologist all of my life, so you can see me up at the top there in my childhood collecting fossils and my Scouts geologist badge. And my mum never tires of telling anybody who listen that when I was 9, Mary Anning, on the right there, was my pin-up. So I was always very keen on geology, and there we've got an example of one of the other organisms, as well as the dinosaurs. These organisms, the ammonites, became extinct. And we also had a lot of marine reptiles being extinct. So Mary Anning, my friend there, she was very active fossil collecting on the Jurassic coast. finding fossils of, you may be familiar with an ichthyosaur, a swimming marine reptile. And also there were plesiosaurs, and even bigger than that, pliosaurs. Callie and I were watching the news the other day, and there's going to be a series coming onto the BBC about the recent discovery of a superbly preserved pliosaur skull that was found on the Jurassic Coast by a chap called Steve Etches. So look out for that. This was a very impressive beast. Also the flying reptiles, the pterosaurs, that they became extinct as well. And in fact, with the vertebrates, all animals weighing over about 25 kilograms became extinct. The ammonites, the curled-shelled organisms, they became extinct as well. So a lot of unrelated organisms. We lost perhaps 50% of life on Earth. So, what's the connection between meteors and dinosaurs? Let me introduce you to the heroes of this tale. Here we have the Alvarez duo. We've got the Nobel Prize-winning physicist Luis Alvarez and his son Walter. And in the 1980, they came up with this Alvarez impact hypothesis. The start of it all was studying a very thin layer, only 2.5 centimeters thick, of clay. And this clay was found at the KT boundary, the boundary between the Cretaceous and Tertiary periods, at a location called Gubbio in Italy. So what was special about this clay layer? What was special about it was that it contained an unusually high amount of iridium. Well, what's so special about that? Well, iridium, a platinum group element, is extremely rare in the Earth's crust, but it's very common in meteorites. And they theorized that the reason why you had this iridium in this layer, which was found worldwide, and corresponded with the time of the mass extinction, they thought that this suggested that maybe we'd had the impact of a meteorite. So that boundary clay, I mentioned, is found globally, and it varies in thickness as well. So if you're in Denmark, it might only be 1 centimeter thick. But if you're around the Gulf of Mexico, it can be up to 1 meter thick. So you might imagine, well, if it's the fallout, if you like, of when you had an impact, then the fallout would be thicker, closer to the site of the impact. So they're thinking, maybe we need to be looking in the Gulf of Mexico. Now, that boundary clay also contained some quartz grains. And these quartz grains were unusual in that they had these lines on them, these striations. And similar quartz grains have been found at the location of places where they'd done nuclear tests, so very big explosions. And they'd also been found at locations of known meteorite impacts. So this massive impact actually distorted the crystal lattice, and we call this kind of quartz shocked quartz. And again, if you look at the global distribution of the shocked quartz, the size of these grains varies, and the biggest grains are found around the Gulf of Mexico. So again, we are pointing towards this as a potential impact site. Now, we've already suggested that with our blue planet, 71% of it covered in water, most of the meteorites probably landed in the sea. But, hang on a minute. The oceans are floored by oceanic crust, which you might remember from one of my previous talks, is made out of a dark, dense, typically black rock called basalt. Basalt has no quartz in it. So the fact that we've got the shocked quartz suggests that the impact was not on oceanic crust, but on continental crust, so rock similar in composition, for example, to granite. Now, it may have actually hit on the continental shelf, so a shallow sea, but it definitely hit continental crust, and we know that because of the presence of the granite. Now, these strange little glassy blobs are what we call tektites. This is found where you get a meteorite impact and it melts some of the rock that it impacts on. The melt is hurled into the atmosphere, and as it falls back, it sometimes gets a streamlined shape, aerodynamic. And these are found in the Gulf of Mexico. So, if we did have an impact site there, and it's in a shallow sea, we would imagine that there would be a significant effect. The numbers here are meters height of waves. So, a massive tsunami, the wave that you get by the displacement of water. Now, that would have created, with this big wave, a surge carrying lots of the sediments from the seabed. So you would have, first of all, the tektites raining down, these glassy little spherules. Then this tsunami, which would have rapidly eroded lots of seabed material, and then a big surge of it would have carried it inland and then dumped it. And the coarsest material, the sandy stuff, would be deposited first. So you'd get thick sandstone layers. Then, as the current died down, you would start to get the finer sands and shales. And there would be a series of pulses of these waves, so you'd get a repetition of those beds. Finally, over a longer period, we would have the fallout, the very, very fine dust coming down from the atmosphere. So that's our sequence of rocks. In 2016, there was a drilling project in this area of the Gulf of Mexico, and it was a borehole over 1 kilometre deep, 1,335 metres deep, and it took them 2 months to drill it, and it cost them $75 a centimetre, so not a cheap project. But the core samples from the centre of where they thought the impact site might be confirmed many of these ideas about it being a meteorite impact site. So what did the Alvarez Geo conclude from this evidence? What story did their evidence tell? They propose a massive meteorite, somewhere between maybe 10 and 15 kilometres across, arriving at the Earth at 20 kilometres per second. Now, relative to the size of the whole Earth, this would be smaller than a pinhead. So be careful when you see all of these graphics in documentaries on TV, or if you look on YouTube or whatever, showing something a quarter of the size of the Earth. It's not. Compared to the size of the Earth, it's tiny. But it would have a huge amount of energy released. Been estimated it would be similar to the amount of energy that would be released if you let off an atom bomb, one bomb for each square kilometre of the Earth's surface, all concentrated at one impact site. So, the asteroid then, big, up in space, the meteor where it's hitting the atmosphere and it's a shooting star, the meteorite when it's hitting the Earth. So we might imagine that we could have a crater somewhat like this. And we think that this is located on the Yucatan Peninsula in Mexico. Now, in the 1950s, they were searching for oil in this region. And they did discover some deposits. And unknowingly, they'd actually hit the debris from the meteorite impact. But they thought it was volcanic rock. Obviously didn't have a very good geologist on board. Now, the crater would have filled with sediments, and the sediments are less dense than the surrounding rock. Now, you might remember from yesterday's talk talking about remote sensing, so using, for example, earthquake waves, seismic waves, as a way of looking inside the Earth, much as we can look inside the body using X-rays. If there's a density contrast, that will affect the gravitational attraction. And using a gravity survey, we're able to identify areas where you have a depression filled with lower density sediments. And indeed, such a gravity anomaly exists about 200 kilometers across, right there on the Yucatan Peninsula in Mexico. Again, in the late 1970s, they were looking for oil in the region, and it was kind of rediscovered by some petroleum geologists. I mean, the geophysicists, they thought, yeah, this looks like a crater impact. But they hadn't looked at all of the evidence. But in the 1990s, Alan Hildebrand shared his information about the shocked quartz and about the tektites and so on with one of these geologists, the geophysicist with Penfield. And they decided, yes, that's it, that's confirmed. It is an impact feature. So what would have happened when a meteorite hit Earth? Hands up, this is speculation, but it's a good story. First of all, we had this massive tsunami flooding all of the coastal areas, possibly going 20 or 30 kilometers inland. The impact of the meteorite would have blasted a lot of material up into the air, possibly as much as 50 or 60 times the volume of the meteorite itself. This would have created global firestorms. That material would have been very hot, so it would have been very, very intense radiant heat. Thousands of square kilometers surrounding the impact site. You'd have spontaneous combustion of vegetation. The burning would mean a lot of soot and ash high into the atmosphere. The impact, lots of very fine material high in the atmosphere. So a cloud spreading globally. And it's thought that for as long as a couple of years, certainly you would have had something akin to what's commonly described as a nuclear winter. So dark clouds preventing sunlight getting to the Earth, reducing photosynthesis, and the collapse of food chains. So the food chains collapse. The flowering seasons of plants get shorter. Breeding of animals completely disrupted. And just to add insult to injury, at the location, Chicxulub, Yucatan Peninsula, a lot of the rocks contain this mineral. This mineral is anhydrite, calcium sulfate, very abundant. This would have been vaporized by the impact of a meteorite, and it would have reduced enormous quantities of sulfur, and this would have gone up into the atmosphere as sulfur dioxide. Why is that important? If you have lots of sulfur dioxide in the atmosphere and it gets dissolved in rainfall, you have acid rain. So if you've got lots of acid rain, so you've got acidic rain falling on abundant calcareous or calcite-rich rocks, limestones, they will dissolve the limestones. And if you dissolve the limestones, the gas that you release is carbon dioxide. So after a few years of global cooling due to a big cloud shutting out a lot of the sunlight, the massive increase in carbon dioxide would have led to global warming. The oceans would become more acidic. So much of the marine life there, the plankton and so on, the base of the food chain would be affected. All of those organisms that have calcium carbonate in their build-up, in their shells or in the coral, would start to dissolve, resulting in even more carbon dioxide being released. So the combined effects would have been completely devastating. Yes, the immediate aftermath would have killed a huge number of organisms. And if the fires, the extreme heat, and the shockwave didn't get you, then the nuclear winter and the subsequent global warming would have done. So it would have been a bit lonely for the ones that survived. Oh, dear me. So these subsequent environmental changes, the darkness, the global cooling, and then the global warming, led to the collapse of food chains and the extinction of many unrelated species, including our friends the dinosaurs. Estimates vary, but even for the simplest organisms, like these photosynthetic algae, it would have taken a long time to recover. Now, these photosynthetic algae, they use more carbon-12 than carbon-14. So a huge amount of them would have died in that mass extinction, and that would have changed the ratio of carbon-12 to carbon-14 in sediments. There'd been a massive increase in the amount of carbon-12 present in the sediments just after the impact. And this corresponds with the increase in iridium, which you might remember is what was found in the boundary clay. And it's, when you look at the data on this, it took over 1 million years for these ratios, the iridium and the carbon-12, to return to the previous levels. But for other organisms, it would probably have taken 2, 5, maybe 10 million years. It took the planet a long time to recover. So all of the evidence seems to suggest then that the Alvarez impact hypothesis for the Cretaceous Tertiary, the KT extinction, is correct. It's widely accepted since the 1980s. But it's not quite that simple. Often, I used to say to my students, there's very few straight lines in geology. Often, if you put two geologists in front of one exposure of rock, they will tell you slightly different things in their interpretation. Remember, the evidence, very often, a lot of it's missing and a lot of it has been changed. You may remember in my second talk, The Wonderful World of Volcanoes, I mentioned the supervolcanoes, the Deccan traps in India, for example. Enormous volumes of lava being erupted. And remember that when you get volcanic activity, it's not just lava that comes out. You also get gases. Indeed, that's where our atmosphere came from, and also where most of the water on the planet came from. Now, the Deccan traps, some of the biggest eruptions in Earth history. And when were they? Between 63 and 68 million years ago. So coincident with the time of our proposed impact. We're talking about perhaps as much as 1.5 million square kilometres covered with these flood basalts. And these flood basalts, in some places, built up through repeated eruptions to sections of rock up to a couple of kilometres thick. So a huge volume of rock, but also a large volume of gas. Some of the commonest gases coming out of the volcanoes: sulfur dioxide, giving us acid rain, and when it's falling on areas of limestone, generating a lot of carbon dioxide. And another big gas coming out from the volcanoes, carbon dioxide. So there's a strong possibility that this is related to the extinctions. And some people maybe doubt the Alvarez hypothesis, and say, well, maybe it's not the impact. Maybe it's actually climate change due to huge amounts of volcanic activity. But if we did have, and there's good evidence that there was meteorite impact, then maybe the effects of that could have been amplified by this. At the moment, we do not know. It's possible that there could have been multiple impacts. Maybe the Chicxulub wasn't the only one. Maybe some of them fell in the oceans, in oceanic crust, and since then they've been subducted, they've been destroyed at the subduction zones, so that the evidence is gone completely. There have been some other large craters identified. So the Baltish crater in the Ukraine, 24 kilometers across, the Silver Pit crater, 20 kilometers across in the North Sea. In 2006, some researchers looking again at gravity anomaly data proposed that they had found the Shiva crater, about 450, 500 kilometers off the west coast of India. And this is actually a lot bigger than the Chicxulub crater. So could it be that this actually triggered the Deccan traps and that then we had the associated climate change? However, the Shiva crater as a meteorite impact site there's a lot of debate about it. It's not widely accepted because there are other explanations for large depressions. So what if it was all due to meteorite impact, and what if that meteorite that landed at Chicxulub just landed a few seconds later in the middle of the Pacific Ocean? Would have landed in deeper water, there'd have been less rock vaporized, less sunlight blocked, less chance of a mass extinction. The dinosaurs might have survived. Well, when we're looking at extinctions, be aware the dinosaur extinction is not the only one. All of the time there are background extinctions going on. A mass extinction, large numbers of unrelated organisms, has happened several times before. We've got 5 really big mass extinctions shown by the spikes on the graph there. And we can look at one at the end of the Ordovician period. 443 million years ago. This would have been triggered, we think, by climate change. So there would have been a glaciation and a massive drop in sea levels. So many organisms living on the shelf seas would have become extinct. So this primarily affected marine organisms, the woodlouse-like trilobites, these shells here, the graptolites, the brachiopods, and the graptolites on the right there. In the late Devonian, about 360 million years ago, we had another mass extinction, again, climate change, with sea level change, with a massive reduction in the oxygen levels in the oceans. Many of the marine organisms died. At the end of the Permian, 252 million years ago, we had the Great Dying. We nearly lost it. 95% of species disappeared. The cause is still debated, but we are fairly confident that it's related to the Siberian traps. So again, to huge amounts of volcanic activity leading to a big increase in greenhouse gases. We then had, at the end of the Triassic, another extinction 201 million years ago, triggered by volcanic activity leading to climate change. And then we have the one that we've been talking about this morning, the end Cretaceous extinction 66 million years ago, probably related to meteorite impact, but also probably related to a lot of volcanic activity and the resultant climate change. Now, there's considerable scientific evidence that actually we are now looking at the 6th mass extinction. And some people have coined the phrase the Anthropocene extinction, because we think it's largely related to us, to human activity. There's a huge decrease in biodiversity. The rate of species extinction today is significantly higher than the background rate observed throughout Earth history. Many species of plants and animals are at risk of becoming extinct, and many have already become extinct. And the human impact is exemplified by the changes in particular in mammals and birds. The leading causes of this species decline, well, we've got habitat loss, so the destruction of natural habitats, whether it's clearing huge areas of rainforest, whether it's urbanization, whether it's increasing the amount of land used for agriculture. But it's also back to climate change and global warming, threatening species by changing the environment, particularly temperature and precipitation. We've also got overexploitation of natural resources, whether it's overfishing or overhunting. We've caused the extinction of many organisms by this in the past. We've also got the introduction of very invasive species, whether deliberately or not. So here you've got this pretty little bird, the Guam flycatcher, which is very common on the tiny Pacific island of Guam. In the 1940s, a ship arrived and accidentally introduced the brown tree snake, which likes to eat Guam flycatchers. Sadly, nobody's seen a Guam flycatcher since 1983. Or a more familiar example, you all, I'm sure, remember squirrel nutkin and tufty fluffy tail, the beloved red squirrels, which are the native squirrels in Britain, largely now displaced by the grey squirrels. The grey squirrels carry the squirrel pox virus, which kills all of the red squirrels. So now, very diminished population, 75% of which is up in Scotland. We've also got the climate change. We've got the ocean acidification going on as we speak. We've got pollution. We've got chemicals in the water. We've got plastics affecting ecosystems. So this is important. Now, while the current mass extinction is not as sudden, not as catastrophic as some of the previous events that I've described, it's unfolding at an accelerating pace. So extinctions are increasing at an increasing rate. Now, the International Union for Conservation of Nature has a thing called the Red List, a list listing the extinction risk of various species. And there are huge numbers of species listed here which are vulnerable, which are endangered. Now, efforts are being made globally to address this. Lots of people looking at habitat conservation, looking at protecting biodiversity, and climate change mitigation. But a bit of a concern that in the first draft of the conclusion of the COP28 conference this week, there was no mention of reducing the use of fossil fuels. So, what have we found out? We found out that asteroids and meteorites come from the asteroid belt between Mars and Jupiter, that most of them burn up as meteors or shooting stars when they hit the atmosphere, and that about 3/4 of them end up in the sea, so we don't see them. We found that there's a 200-kilometre wide impact crater on the Yucatan Peninsula, the Chicxulub crater on the edge of the Gulf of Mexico, that there's a lot of evidence from the fallout layer, the boundary clay, the iridium, the shocked quartz, the tektites, the tsunami deposits, the geophysics, that this is an impact site. But we've also added in the importance of flood basalts, huge amounts of volcanic activity leading to an increase in greenhouse gases and climate change. And we've also considered whether we're actually causing the Anthropocene, the 6th extinction. So, sorry not to be more cheery. After all of that doom, gloom, death and destruction, I'd like to, on a lighter note, leave you with one of my favourite cartoons. So thank you to the techs, thank you to you for coming, and especially to those of you that have seen a number of my talks. You could entertain yourself with looking at past talks if you've missed some while you're doing your packing in the cabin. So thanks again, and if you do have any questions, I will be at the back to answer them. Fantastic. Thank you very much.